We'll go ahead and get started with Atomos.
Thanks for the invitation to come talk here today. So, my name is Vanessa Clark. I'm co-founder and CEO of Atomos Nuclear and Space. So we're a space-for-space company. We are focused on the in-space transportation and logistics market. So I've worked in the aerospace industry since graduating in 2011. So I've worked for a couple of large aerospace corporations and in agencies. So I worked for the German Space Agency, DLR, in advanced concepts for interplanetary, including nuclear electric vehicle concepts, and also in their launch vehicle division. I also worked in the launch vehicle division of Astrium, now called Airbus Defence and Space, or Ariane Group. The group was split in half. And then finally, I was at Lockheed as a propulsion technology lead and also a program manager, leading the largest subcontract on the Orion program. So our team has recognized a fundamental problem with the space industry. That's transportation cost. This is creating a bottleneck and a barrier for entry for new players. So you're probably aware that there's a mini revolution going on in the space industry, lowering manufacturing and operating costs for satellite operators. But cost of access to space remains a problem. So cost to deeper orbits, in particular the lucrative higher orbits such as MEO and mid-Earth orbit, and geostationary Earth orbit remain prohibitively expensive. So a lot of the new launch providers are optimizing cost to low Earth orbit. However, operators who want to gain access to geostationary Earth orbit aren't seeing these benefits. This is because we have limited space transportation infrastructure. The only way we can get to and move about in space is really using rockets. So at Atomos, here is our proposition. We are building a space tug. This is a satellite that can move other satellites. This will enable lower cost because the system will be reusable. To enable this, we need two things. First, we need more efficient rocket engines that are optimized for in-space transportation only, unlike rockets. So these engines need very high specific impulse, and the way to do this is through electric propulsion. These, of course, need a power source. So we need high-density, lightweight power systems for space applications, which is why I'm talking to you all here today. So looking at space power systems. So with solar electric power, if you want to increase the power levels, you just add more panels. So if you move to larger power levels, you have the same specific mass. So this is the kilowatts output. Sorry, this is the kilograms required to produce a certain power. If you look at other power sources, such as nuclear fission, we have a pretty good relationship. As we scale up the power levels, the specific mass of the system drops. So at around 100 to low 200 kilowatt electric, we have a crossover point at 1 AU, so the distance of the Earth from the sun, where nuclear fission becomes a very, very viable option in terms of mass. So this is for certain fission power systems, so you'll notice that NASA Killer Power System is designed to operate and be optimized for lower power levels, so it actually has a much higher specific mass. Radioisotope thermal generators also have a worse specific mass, particularly at higher power levels. So for low mass transport between low Earth orbit and geostationary Earth orbit, we can get away with tens to low hundreds of kilowatts electric. So solar is a very viable system for this. However, if we want to target more markets, such as the super heavy geosatellites, telecommunication satellite, military assets, or if we want to look at ride sharing, should really go to a higher power level. So nuclear here is clearly the best option. Once we have this type of power system, it also has other applications in space. So for industrial applications on the lunar and Mars surface, we really want hundreds of kilowatts and megawatts of power. So for example, this is the power requirement of processing propellant at the poles of the moon. If we want to do human spaceflight, we can increase the power levels even more. So with a system that's in the tens of megawatts, we can get to Mars faster than we could with a nuclear thermal rocket engine or obviously any chemical solution. Another reason why we're looking at nuclear at our company is the size of the spacecraft. We'll be rendezvousing with assets and performing proximity operations. So we need a vehicle that has great controllability. So a comparable solar electric propulsion system, so that's SEP, is going to be a lot larger than a similar nuclear vehicle. So the nuclear system that we are developing consists of an approximately 1 megawatt electric system. So we're using low-enriched uranium, so it's highly moderated, it's non-weaponizable, using the new generation of fuels that have been developed in the past decade. It's gas-cooled. We want to keep the cycle simple while having resiliency and redundancy. Another key aspect of this, which is also very interesting for the terrestrial power market and aviation, particularly electric aircraft market, is a power management and distribution system. We're producing a lot of electrical power in a relatively small spacecraft, which we have to manage and distribute in a very effective way. So the power converters that we are developing will be applicable to terrestrial applications as well. We're proposing a modular architecture so that we can use this not only in our spacecraft, but today's and tomorrow's commercial spacecraft that require high power levels. So in summary, so this is our system versus a solar electric system in the near-Earth environment. We have 4 times the capacity. So the exact difference is subject to optimization of the specific impulse of the engines. But essentially, this means we have 4 times the revenue-generating potential of a nuclear electric vehicle in comparison to a solar electric. It's the same for the moon. If you're transporting payloads to the moon, we have 4 times the capacity. So if you move away from the Earth and use higher power levels, we have 12 times the capacity in comparison to a solar electric vehicle. So obviously very interesting for NASA. So the business case. So our primary beachhead is in-space transportation services, targeting today's most lucrative orbits. So today, a launch without Atomos involves a large rocket launch from a limited number of launch sites. These are normally equatorial. Satellites targeting geostationary Earth orbit, in most cases, have to maneuver to the final position, which requires sometimes 50% of the mass of the satellite to be dedicated to propellant, instead of revenue-generating payloads. So launch with our service, a satellite operator will be able to use a smaller, more cost-effective, or reusable rocket from any launch site in the world. Our spacecraft will rendezvous with them and take them to their final destination. Precision place them so they won't need to carry their own propellant. They probably won't even need apogee raise engines, which is a big technical risk for satellite operators. So we have a dynamic pricing model because of large profit margins. So we enable any launch provider to access basically all of these space transportation markets, from small satellites to large satellites, provided they want to go to orbits beyond LEO. Initially targeting just 1 customer contract in our first year of operation, by the year 2030, we'll be targeting 5 operators. So once we enter the LEO to GEO transportation service, we can also diversify our services and provide end-of-life removal for satellites, which is a legal obligation for a lot of the in-demand orbits. And finally, we can perform recovery services. Approximately once every 2 years, there is a commercial satellite that is placed into the wrong orbit that is then a wasted asset. The current go-to-market strategy. So we are currently developing and fostering relationships with our target customers and partners. In the next 12 months, we'll be taking take-or-pay contracts from those future customers. So we'll be looking to work with the government on this to support some of the development costs. However, saying that, we do aim to be a commercial company. So in terms of technology development, there is obviously a lot of technology that's going to go into this system. A lot of it is already under development, and some of it is already being used today. So a lot of the things that we are developing in-house are immediately commercializable. For example, as I mentioned before, the power management distribution system, consisting of very high density, resilient, robust, and radiation tolerant converters and harnessing. We'll implement this in a demonstration mission, which we will also use for commercial purposes to capture the lower capacity market and low Earth orbit markets in a solar electric propulsion vehicle. So we'll have as much commonality between the vehicles as possible. So once we demonstrate our power electronics technologies in space, we'll license that technology to other providers who will be able to manufacture them en masse for terrestrial markets. Also enter other markets with our subcomponents before launching our full workhorse vehicle in the mid-2020s. After on-orbit demonstration, we'll be able to license and sell the nuclear reactor technology in space and on Earth. So the market that we're currently targeting is quite large. So LEO to GEO transportation is today around a $3.6 billion market. There will be new emerging markets in the next decade, including debris removal, which is a growing problem. But we're targeting to set ourselves up to be the primary players in the cislunar market. So cislunar is anything from the surface of the Earth to the surface of the Moon. So power and propulsion transportation are obviously going to be a large part of this nearly $3 trillion market. We're not the only company targeting in-space transportation. We actually have a healthy number of competitors. However, we are the only company who believe that high delta V capability, so that is great reusability and high payload capacity, is the key to success in this market. So our real competitors right now are alternative solutions, such as SpaceX and United Launch Alliance. Fortunately, we both bring value to companies like that. We extend their markets, we increase the cadence that they can launch at, and we increase their market capture. So 2018 is a great time to enter this market. So not only do we have a growing space market, we have a growing discrepancy between the launch vehicles that can address those markets, which we're taking advantage of. Secondly, in terms of the technology development and technology cost and risk, we heard RPE's presentation this morning. A lot of the technologies that they're focusing on and are funding the development of are what we need in our system. Furthermore, the US government is working to streamline the regulations approach for reactors. There are a couple of nuclear companies in the US who are startups who have voiced their concerns that the process is too cumbersome. So the Nuclear Regulatory Commission is looking to bring the process timeline down by more than 50%. So we're taking a $100 million approval process and trying to make it less than $10 million. So we do have an initial development period, but after several years of operation, we do have great revenue. As I said before, this is a $3.6 billion market opportunity. So these revenue streams are really with just a handful of customers. So the founding team, so I spoke to myself. I have an aerospace and program management background with experience in nuclear electric propulsion and spacecraft systems engineering. So I've brought two co-founders on board from the business side of the house. So firstly, I have taken William Kowalski from the finance industry. So he's our analyst. He's been performing data analysis, looking at the space transportation launch vehicle industries, and also any industry whose growth would lead to the growth of the space transportation industry, such as the Internet of Things, such as Earth observation. So he's also leading the policy and regulatory affairs side of the house. So I also brought Brandon on board. So he has led a couple of startups, high technology startups from ground zero to scalability. But we know that we can't do this alone. Obviously, there are some key challenges. Most of these aren't actually technical. These are regulatory, these are supply chain, and these are market. So I've established a brains trust to help us with these aspects. So I have Aris Kandros, who is the former CEO of Westinghouse Electric, as well as Regis Matsi, who is the former CTO of Westinghouse Nuclear. So these two powerhouses are helping us with the regulatory process and the supply chain, as well as safety, and making sure that we have a competitive IP strategy, particularly in the face of the large aerospace primes. So we also have some space advisors. So Tom Garner was the former chief engineer at Moon Express, and Steve House, who you're probably familiar with, was the former director of the Center for Space Nuclear Research at the Idaho National Laboratory. So the impact. So for space transportation, we allow more rocket reuse, which flows down to the satellite operators with lower launch cost. Our power systems will also enable more powerful payloads and more revenue to be generated per satellite, which is great for the space environment and also the space data users. I said before that our modular solutions will be able to be spun out into the aviation industry, reducing costs and CO2 emissions. But finally, and more importantly, we enable high delta V capability missions, which is something that NASA is very interested in, as you probably all heard yesterday in Lee Mason's presentation. So in summary, we want to, through commercial avenues, enable deep space transportation. So our current asks is we are starting to seek public-private partnerships. We want to use your expertise. Secondly, we need your help and support. Obviously, there are a lot of regulatory and policy concerns. We need ARPA-E, DOE, and NASA to tell decision makers in the agencies and in government that space nuclear is safe, which it is. Space nuclear is safe, and that it is enabling, and is going to enable America's competitiveness and superiority in defense and space exploration. Finally, we are actually raising our first round of investment, so we are seeking investors to close out the round. So thank you, and with that, I invite any questions.
Hi, Vanessa. Have you heard of IOStar?
Yes, I have.
Okay. So this is a concept that was considered previously, and there are, you kind of hit on some of the safety concerns, right? Because it's a tug, right?
Yes.
So operationally, you'll be bringing an active reactor back towards Earth in geospace.
Yes.
And so there are going to be concerns from the public. Whether or not they're valid, that's going to be a concern. So what power level, were you looking at the 100 kilowatt electric as the system you were planning on utilizing for this tug system? Because it's pretty big.
Yeah, so we're looking at higher power levels. So we want to have the advantage from specific mass, which we can only get at the higher power levels. So 100 kilowatts electric, we would address with our solar electric vehicle. So we're going to have a diverse fleet of solar and nuclear vehicles.
Okay. So the concerns I have with the nuclear is the 1 to 300 kilowatt electric system that Lee Mason and I worked on JIMO. You did show it's 30 meters. It's the size of a football field, and I think we assumed 5 launches, right? And on 3, well, we were assuming maybe a heavy lift launch vehicle, which we will have. So there's a lot of on-orbit assembly for it. There's a lot of the other thing is relative to having a reactor near a payload. Is there a lot? Do you have concerns or any calculations about radiation relative to any of the payloads that you would be tugging?
Okay, so great questions. So the drawing that we had was actually really based on JIMO, so we can talk more in detail about the designs in the impact tables because it is ITAR controlled. So yes, so that's not going to be the final embodiment. We'll actually have smaller radiator area than the JIMO vehicle. So firstly, we're aiming to have a smaller spacecraft. We also have a target specific mass. So if the vehicle, if we go through technology development and we realize specific technology risks that mean that we have to have a higher mass vehicle, then we will have to look at modular on-orbit assembly. So currently we're looking at 2 strategies. So we're talking to various launch vehicle providers. We could potentially launch this in 1 launch, given some of the new commercial launch vehicles that are out there. But we'll also have a vehicle that has the capability to rendezvous and dock. So the current baseline scenario is launch in 2 modules with the propellant tanks and thrusters in a separate module, which will enable us to change out the thrusters as the technology matures, because cathode life of electric propulsion systems is also a key concern. So I think that were the 2 questions you asked.
Yeah, the radiation relative to people wanting you to come near their assets.
Yeah, absolutely.
How do you ensure that whatever radiation protection you might have relative to their assets?
Yeah, so we will always approach the target payloads from the shielded direction. So when we're doing proximity operations closer than 1 kilometer, we will be approaching with them in the shadow shielded area. Now, we'll also be powering down the reactor, which it won't be instantaneous, but once we're in the proximity field, we will be doing that. Secondly, customer discovery. There's really only one group of people who is very, very concerned at the type of spectrum that we're saying that we'll have for the duration time that we're proposing, and that's missions and systems like the James Webb Space Telescope that have very sensitive CCDs, which really is no commercial customer. It would just be for special government missions.
Okay, thank you.
Do you have a target reactor for this yet?
We do, and I would love to tell you more about it during the impact tables.
How much money do you think you need to get to a prototype demonstration, let's say?
Yeah, so we'll be raising in tranches, so the total capitalization needs for us will be approximately $80 million for this. So that will be offset by, hopefully, government funding, which will bring down those needs. We're also relying on our partners, suppliers, and customers to offset those costs. So in particular, the ARPA-E new initiative, most of the companies who were awarded contracts through ARPA-E are part of our supply chain. So the technology development that ARPA-E is funding for the future of small modular reactors is directly applicable to our systems. So a lot of the technology risk will not be paid for by us and our investors. So also, having said that, we have some great opportunities for cost sharing. So for example, launch insurance providers really want to have a way, so a backup option from a multi-$100 million or billion-dollar payout. As I said, there are incidences with a cadence of once every 2 years where a satellite is placed into the wrong orbit. So this costs an insurance broker or underwriter hundreds of millions of dollars, whereas our service would only cost tens of millions of dollars to recover that asset. So there are ways to have this financed by customers.
Are there other supply chain issues that you see coming up, or what are going to be key pain points in the supply chain?
One thing that is potentially a pain point is the geopolitical concern of the fuels. We're looking at a specific fuel that is currently not manufactured in the US. So I'd love to have that conversation with you to see if, I know that there are initiatives to set up a manufacturing plant here. We'd like to have more confidence in that.
So two-phase flow in space is going to be a problem, and in the ground they have a lot of data that they get. Where are you going to get that data in order to make your reactor efficient in space?
We're not going to have two-phase flow. So that with the technologies that we're choosing, we want to burn down as much technical risk as possible before we launch a system into space. So we are not using a liquid metal reactor or a Rankine conversion cycle because we could not vet that out on Earth.
Well, so I've been doing studies like this for a long time, and all the studies that we did in the past always assumed highly enriched uranium. That was the only way to get down to those low specific masses that you're pursuing. And I realize the reasons you're thinking LEU, but it comes at the expense of mass and efficiency, right? So how are you going to get through that?
Yeah, so it's a great question, and it's why we're at such high power levels. So there is a point where you have convergence of HU and LEU systems. It's because of the shielding, it's because of the supporting structure, it's because of the reflector. At high power levels, there isn't that much of a difference in specific mass between LEU reactor and a HU reactor. Above 1 megawatt is not the reactor that's the mass driver for a system like this, it's conversion. So we feel that we can have the specific mass you could get with the HU system, but with the LEU system, which is really what is enabling our company.
Can you elaborate on your power management system? What do you have in mind? I mean, I'm looking at your white paper, so you have some ideas there.
Yeah, so we can also go into more detail in the impact tables, but essentially we have 3 options. The leading option right now uses a new substrate material. We're looking for a DC power system. So the pain point here is the DC to DC power conversion, which typically has very poor efficiency. So we have a lot of waste heat, particularly at 1 megawatt electric. And also it can be quite difficult to integrate, and it would be a one-off system. So we're looking at a modular system with small modules that can scale up from tens of kilowatts to 1 megawatt. And the thing that will enable this is the new substrate that we're looking at. I want to talk to you in detail about it. Having said that, we have a couple of alternatives that NASA and Sandia were looking at in the mid-2000s. I see your expression. I'm sorry I can't go into more detail, but this is ITAR controlled, and since we're live streaming, I'm going to defer the conversation.
It's in your concept paper.
It was, and the restriction and the circulation of that paper was restricted to NASA's and ARPA-E's partners, who are American citizens. Sorry about that.
Hey, can you talk a little bit more about some of the other potential users for this technology that aren't space tugs? I mean, obviously there is a potential market out there for space mining. Have you pursued those folks? Because those are the ones that might need megawatts.
Yeah, absolutely. So there are a couple of companies that are looking at space mining, and they need hundreds of kilowatts to megawatts. And so this is a system that would enable them. One great use case is the study that you are also involved with, which is United Launch Alliance's Propellant Depot. So they need a lot of electrical and thermal power for sublimation of regolith and electrolysis of propellant. So to produce enough propellant, so hydrogen, oxygen, to support a cislunar economy, you're going to need hundreds of kilowatts to megawatts. So with 3 of our reactor modules, they'd be able to support any propellant needs within the next 20 years. So mining and in-space production are also other applications. So we're talking to those companies. Their eyes sort of light up when we say the power levels. They're like, oh, we never thought we'd have that much power. Oh, we want to see how that scales our production output. So it's fantastic for lining, electrolysis, and also regolith sublimation.
How about terrestrial applications? You'd mentioned that as a spin-off. What do you see there?
So a lot of the technology development that is required for our system is also required for small modular reactors. So we're talking the new moderator materials, the reflector development, the automated control systems for the reactor, because obviously we don't want to have a ground staff of 300 who don't have a constant data stream to the reactor. So those key pieces, which were outlined earlier today by ARPA-E, will all be needed in our system. And so some of those select pieces will be part of our core competency, and we'll be licensing those to terrestrial reactor operators to use in their systems as well. So we probably won't have the production capacity to be a supplier for terrestrial applications, but we'll have the technology that can be spun out into it.
Do you have a target reactor cost?
We do, and that's between $8 and $20 million production cost. So that's materials.
For which size reactor?
So that would be around 1 megawatt electric.
Okay.
Thanks very much.
Okay, thank you.